Hi, my name is Yannis Kasdaridis and I will present you our demo work with the title A Novel Architecture for Semi-Active Wake-Up Radios Attaining Sensitivity Beyond -70 dBm. This is a joint work with my colleagues Nikos Sidiropoulos, Ioannis Zografopoulos and our professor Thanasis Korakis. In order to surpass the limitations of the widely adopted duty cycle networks, researchers have proposed the engagement of an auxiliary receiver, the so-called wake-up radio, dedicated to awake the host node only when required. Typically, semi-active wake-up receiver implementations employ an envelope detector that harvests RF power by their antenna while using a nanopower comparator to decode the transmitted wake-up signal, usually modulated using the on-off kink scheme. Our finding lies in the observation that the sensitivity of the wake-up receiver is solely dependent on the characteristics of the comparator being used. More specifically, on the input offset voltage and the input bias current of the comparator. It is worth noting that the best obtained performance in semi-active wake-up systems in terms of the achieved sensitivity is presented in the work that you can find below, with the reported sensitivity at -55 dBm while drawing roughly 600 nanoamps. In our work, we propose the employment of a nanopower amplifier that identifies the harvested signal prior to the final decoding by the comparator. Following this principle, it is possible to detect ultra-low RF signals achieving a sensitivity beyond -70 dBm. In this picture, we see the implemented prototype node that features the nanopower amplifier, the nanopower comparator, and an ultra-low power microcontroller, which is dedicated to check the incoming packets for the correct wake-up address prior awaking the host node in order to avoid false wake-up signals. Our prototype features a blue LED that blinks when receiving a wake-up packet. Actually, the blue LED is directly connected to the comparator's output, thus visualizing the actual received signal. Moreover, a red LED illustrates that the correct address is received and the while LED turns on when the host microcontroller is awakened. Let's now proceed with some real experiments. In our first experiment, we connect the prototype node with a LoRa transceiver used to propagate the wake-up packets with the aid of a fixed attenuator. We observe that upon the reception of a wake-up packet, the blue LED blinks respectively to the signal acquired. When the transmitted address matches with the receiver address, the low-power microcontroller awakes the host microcontroller, while in a different case the low-power microcontroller returns back to sleep. In order to characterize the sensitivity of the receiver, we first measure the TX power of the LoRa module by using a spectral analyzer with the aid of a -8 dBm attenuator. We repeat the same experiment, but this time we add a series of fixed attenuators in order to drive the receiver with wake-up signals of -70 dBm. We observe that even at these low-power radio signals, the receiver is able to decode the obtained packets and correctly match the given address. Next, we connect the outputs of the operational amplifier and the comparator circuits with the probes of an oscilloscope in order to visualize the obtained signals. The yellow line illustrates the output of the amplifier, while the green one of the comparator. Apparently, the obtained signals follow the exact pattern of the on-off kink signals transmitted by the LoRa node. In order to characterize the power draw of the developed receiver, we utilized the current ranger power meter. The meter is connected so as to measure the power draw of the amplifier, the comparator, and the low-power microcontroller. We can clearly see that the power draw of the receiver, when in quiescent state, is roughly 470 nanoamps. Next, we disconnect the LEDs and we measure the power draw when receiving a wake-up packet. During the reception, the low-power microcontroller is awaking, consuming roughly 300 microamps, which is the same with the state-of-the-art implementations. In our last experiment, we employed two nodes in order to demonstrate the address matching capability. Apparently, both nodes receive the wake-up packet, but only the node with the correct address awakes its host microcontroller, as illustrated by the white LED on each node. We repeat the same experiment by adding a series of fixed attenuators in the antenna of the LoRa transmitter. Notably, in all previous experiments, we employed wake-up packets with very low transmission rate for visualization purposes. However, our receiver is able to support signals transmitted at 100 bps. To this end, we repeat the last experiment by reconfiguring the nodes at higher speed in order to illustrate their capabilities. Please note the blue LEDs that blink quite faster when receiving a wake-up packet. In our prototypes, we have tested several operation amplifiers and several comparators, each one with different power draw as noted in the illustrated tables. Notably, when using the TLV3691 comparator, the supported sensitivity was roughly minus 57 dBm, while when using the TLV7031 comparator, the sensitivity can reach beyond minus 70 dBm. It is worth noting that in all different combinations, the power draw of the developed receiver is equal or even less with the state-of-the-art semi-active implementations. Thanks for watching. If any questions, please let me know.